This is a fun projectile motion problem. Here we have a bullet that's fired horizontally off of a vertical cliff. And what's so great about this problem is you can actually take these measurements of the vertical height and the horizontal displacement to determine the muzzle velocity of the gun. So this is an experiment you can actually carry out. So why don't you pause the video and try solving this problem yourself if you like, and then play, and I'll show you my solution. Aloha, I'm Linda. I'm the physics coach. And I'm here to share with you some solutions to problems. So, okay, let's get started. Okay, so the problem we're going to do is what I showed you already, and maybe you solved it. So this is the basic idea, is that we have a bullet that's being shot from a vertical cliff, and it's only in the horizontal direction. As it falls, it will gain speed in the vertical direction. So it's a two-dimensional projectile motion problem. But you can see that the height it descends is not very great compared to the horizontal displacement. This is a cool problem, as I mentioned, because you can actually carry out this experiment. This is how the muzzle velocity of a gun can be determined by measuring actual distances. So it's very cool. Okay, so the first thing we want to do, let me zoom out here with I'm old school. I know I should use a tablet, but I actually just like writing. Make sure you always have a protractor or something to draw with and a good eraser, and I use a pencil. You could use a tablet. I'll switch to that eventually. So the first thing we want to do solving a problem like this is determine what the givens are, or what we already know. And you can see in the diagrams that we're given the displacements in the y and x direction. So I always like to write my givens. And let me just check how that's recording. Oops. Okay, so when you read the problem, scan it with your pencil or whatever you're using, and circle whatever is significant. So a bullet's fired with a horizontal velocity, so that means it's just being shot like that. It's a vector from the top of the 80-meter high cliff. Okay, so what's that? That's going to be my y initial. And I always include the units. Okay, don't, if you take shortcuts, then it typically leads to mistakes. Now, before we move on, what's y final going to be? It's down here at the bottom, right? So we know already, without being told the information, that y final is 0. And sometimes that's a problem with reading problems, because you're not explicitly told information. You have to extract it from the narrative. So this is a story, and we're translating the story from the narrative to data that then we can use with equations to determine the unknowns. All right, so let's continue. The bullet strikes the ground 1330 meters from the base of the cliff. So we'll take the base of the cliff as the 0 point of the axis in the horizontal direction. So then we have x initial is 0, right? And then x final will be 1330 meters. So over a kilometer. I use not, that means that t equals 0 instead of initial, because I have a hard time making the little I neat, and it drives me nuts. Okay, what else do we know? We know that in the x direction, there's no acceleration, and that's because we're ignoring air resistance, right? There's no forces acting in the horizontal direction, so the acceleration 0. In the y direction, however, it depends on, we know gravity's acting, but the sign of our acceleration will be determined by our coordinate system, and I'm just going to take up as positive as a default. Okay, so if we're taking up as positive, oops, then that means our acceleration, which is in the downward direction, will be negative 9.8 meters per second squared. What else do we know? You know what? I think that's all we know, right? we don't know the time, which we can find, and we want to find out the initial velocity. Oh, we do know one other thing. What do we know about the y component of velocity to begin with? We know that the y velocity to begin with is 0 because it's only shot in the horizontal direction. There's no vertical component. And we also know then that the x component is just the total initial velocity, and that is what we're looking for. Alrighty, I think that's it. We can find all kinds of juicy things from this problem. We can also find the time, and we can find the final velocity. That's another question that this is an old exam problem of mine, actually, and it was multiple choice, but I took that off. So you can ask what's the initial velocity, what's the time of flight, and what's the final velocity with which it hits the ground. And it's not 0, which people erroneously think sometimes. So I'm gonna redraw everything because I like to draw things. All right, so I'm going to use my protractor. And if you're following along and you have a tablet, go ahead and use your tools to draw this out. And the more advanced you get in physics, the more you'll discover that you can solve a lot of problems just from the diagram. So we want to get good at drawing the diagrams because it's a problem solving tool to analyze the data in the diagram. Trust me on that. Okay, so we're going to take this as the positive y direction, and that's the positive x. And then we'll just arbitrarily select that as y initial. And I'm going to draw my little velocity vector there. There's my v naught initial, and it's going to go like this. So just kind of draw the trajectory like that. And that's the best I can do. So the final velocity, again, it's not going through the ground, but we draw the final velocity vector as if it was going through the ground. So you could just see that's the velocity with which it hits the ground. And this would be the angle like that, if we're asked to solve that. And this, I like to use deltas because I'm lazy and I hate subscripts. So, I write my kinematic equations in terms of deltas as well. It doesn't always work. Sometimes you have to separate out the initials and finals. But from my data, I can already see what the delta x is, right? So it gains displacement. So delta x, which is final minus initial, will be positive 1330 meters, and delta y is final minus initial is negative. It has a negative displacement, negative 80 meters. Okay, that's everything we know. So how are we going to solve this puppy? Well, we split it up into the x and y directions because I don't know the time. I mean, if I go look at my kinematic equation sheet, so this is an equation sheet that I give my students, and we can see it here. So on the right-hand side, these are all the translational kinematic and also some dynamics and energy equations, and then these are the equations on the right, and this is for an algebra-based course. So what equation can I use? I don't know time. I'm going to have to find time. Can I use this equation alone to find the velocity? I don't know what the final velocity is total. So I cannot use this. And I can use this for both the x and the y directions. I'm going to use this to find the final velocity, but I'm going to use this to find the initial velocity. So I'm going to use the delta equation. Now, even though I just have this in terms of x, this works for any direction, right? This is a generic equation. It could be delta x equals vx naught t plus 1/2 ax t squared, or swap off the x's for y or z or q or whatever direction you want. So that's what I'm going to use. My strategy is to use delta x equals v naught t plus 1/2 at squared. This is generic, right? And I will customize this in both the x and y directions to solve this. So I like to just organize it like this. I have my x stuff. So what do I got? I have delta x equals vx naught t plus 1/2 ax t squared. Now I know that the acceleration in the x direction is 0, but I like writing it because it's so gratifying to scratch it out and put 0. So this is the answer I have. We know that Vx naught is indeed just the total initial velocity to begin with, right? Because it's just horizontal. So this is going to be V naught will be delta x divided by t. Okay, but I don't have t. So where do I get t? I get it from the other direction. That's how it works, right? It's always like that. So I go to my y direction and I write out delta y. So I'm customizing this generic equation that Galileo gave us in terms of y now. So, and I put all the subscripts in, so I get Vy naught t plus 1/2 ay t squared. Now, luckily, the time is the same for both directions. Let me zoom out a little now. Right? That's the connector. The time of flight is the connector between the independent x and y directions. So I get to scratch this out. It's very gratifying because the initial velocity is 0. If it wasn't, we could still solve the problem, but it would be mathematically more complicated, and we'll do that another time. So now I can solve for the time, right? I need the time to put it in here, so I can determine what the initial velocity is. So let's just go ahead and do the algebra here, multiply both sides by 2 and divide by ay, and I do some little switcherooning in my brain, and I get delta y times 2 divided by ay 1/2. That's my algorithm for the time. And so now I can put in the quantities. And I'm a big writer. See how I write really big? I broke my finger and I have to like draw like a caveman. Okay. So my delta y, like don't cheap out. Delta y is negative, but that's okay. It's going to cancel out ay because ay is negative as well. So you want to make sure you're very consistent and always like, don't take a shortcut, which often students do, and it gets them into trouble. Just plod on through methodically. It's amazing. We got to the moon with this stuff, so it works. And then minus 9.8 meters per second squared. Always include the units because we're going to do unit analysis to make sure that we're doing it right. It's our only check is unit analysis. So go ahead and, well, I'm going to just do the calculation. I need to pause, but you can pause if you want. So I got my calculator and I'm going to do the square root of 2 times, okay, now I notice these guys cancel, so I'm going to cancel them out because you can't have the square root of a negative number. That would be a problem. Divided by 9.8, close parentheses, and I get, can you see that? 4.04. I'm going to keep an extra digit, right? We always want to keep an extra digit for intermediary calculations, whatever that means. All right, so it was 0 or 1 seconds. So it took 4 seconds for the bullet to land, about 4.041. Let me clean that up. I have a hole in my table. There we go. There we go. So 4.0441 seconds. Now we can use this over here. So I get V initial equals the total displacement is positive 1330 meters divided by the time, which is 4.041 seconds. And now let's punch that into our calculators. And I just take what I found and I don't know, 1330 divided by, go grab that number from my calculator and I get 329. Well, it's 329.15, but we're only going to keep 3 sig figs because we started with 3 sig figs. So it's 329 meters per second. And that's our final velocity. So we found both the time and the initial velocity. Now, as an exercise you can do on your own, you can take this algorithm and put it in here and not even bother to calculate the time if you don't need it. And then just use the measured values to find the initial velocity without having to find the time. And you could prove to yourself you get the same answer. And that's it. Now, if you want to find the final velocity, then you can try that on your own, or maybe I'll solve that later with you, but I recommend using the squares formula. I call it the squares formula, this one here. So you can find the velocity in the y direction that's gained as the bullet falls using this. And then, in fact, I'll just show you this. I worked it out earlier. So you can, well, maybe I'll just do it really quickly. Let me just do it for you. This is a very casual YouTube channel. This is actually the first video I've made for y'all. So, okay, let's go ahead and find the final velocity. So we want to find this final velocity. And remember, the magnitudes of the velocities are always positive, right? Even though it's moving in the downward direction. The fact that it has a negative vertical component of velocity is determined by the angle, which we should get a negative angle, because remember, positive angles are counterclockwise and negative angles are clockwise. So let's see if that works out. So I know this is also the final velocity in the x direction, right? Oops, I got to zoom in a little bit. Because there's no acceleration happening. So the velocity final in the x direction is the velocity final in initial, because there's no change. So we don't have to find any change in the x direction. We need to find the velocity gained in the y direction. So we can use a squares formula. So we have v squared equals v final squared in the y direction equals v initial squared in the y direction plus 2ay delta y. And make sure you're keeping the subscripts. I know it's annoying. It might be tedious for you, but it's bookkeeping. A lot of physics problem solving is bookkeeping. So now we can simplify this because we know that in the beginning, there was no component of velocity in the y direction. So we can strike that. So gratifying. And then I can find the final velocity. Remember, when you take a square root, you get a plus or minus. So I take the square root of both sides, then I get 2ay delta y. That's my algorithm. Now let's stick in the values. I'm going to keep the negative. Now that seems arbitrary, but we always, want our solutions to agree with the narrative of what's happening, the event, right? We know that the y component from inspection will be in the negative direction, and that's not cheating. This isn't a math class. It's sloppy. So we're going to pick the negative, and we get negative 9.8 meters per second squared. And don't forget to include the units. Oh yeah, I forgot to do unit analysis over here. I'll come back and do that in a minute. And then the delta y is negative 80 meters. And then we get to the 1/2. So we have a negative and a negative. They cancel out, thank goodness. So no problem. And let's go ahead and punch that out on the calculator. Square root 2 times 9.8 times 80. And I get negative, what did I get? Like 39.59, which is 39.6, right? Negative 39.6 meters per second. And so let's just check out, I boxed all my answers just to keep track of them so I don't lose them. Notice we get meter squared, per second squared. So the unit analysis would be meter squared per second squared square root, which turns out to be meters per second. Check, check. Now you may say, oh, it's obvious. Why do I have to do it? Well, wait till you take the next semester and you're doing these crazy electromagnetic equations. And the only way to know you're doing it right is to do a check. Now back on this one, you can see here, we have a meters over a meters per second squared. So let's go ahead and check that out. That's going to be meters per second squared to the 1/2. And then those cancel. The seconds come upstairs. And that's a seconds, checkity check check. Right? If you have a good teacher, they're going to ask you to show this. Because that's a good skill. Like, honestly, probably 50% of all new research is just like unit analysis. So it's super important skill. Okay, now how do I put this together to get the total velocity? Because this is only the y component of the final velocity. So I will use the rules of vectors that the final velocity total is Vx final squared plus Vy final squared, yeah? And then to get the angle, I'll use the inverse tangent of Vy final over Vx final. Okay, so let's go ahead and do that. And I get, all right, so we got to keep the signs, especially when we get to the angle. So I have for the x component, what I found out from the first part. And then notice how the x component is so much greater, because it's a bullet being fired. And this is just falling under free fall, so it's not the same. Let's go ahead and get that. And so I have the square root of 329 quantity squared plus 39.6 quantity squared, close parentheses, and I get 331 meters per second. Look, it hardly picked up any speed at all. Yeah, went from 329 to 331, so that y component didn't contribute much. And then the angle, we'd expect that the angle should be teeny tiny, right? Because there's not much of a y component compared to the x component. So let's see if that's true. And again, it's measuring as a negative angle, so we want to make sure we keep the negative sign. And if I'm going too fast, feel free to pause. That's the beauty of YouTube, right? You can pause and go back over, etc., etc. So let's go ahead and do an inverse tangent. And I'm going to go negative 39.6 divided by 33. Ta-da! And I get a negative 6.82. 2222. So very shallow. But if you have a gun and a bullet, you could go to a cliff, shoot it off, just don't hurt anybody or yourself, and determine the muzzle velocity of your gun. It's kind of cool, isn't it? Well, I hope you found this useful, and I hope you come back and enjoy more physics solving problems with me. Well, thanks for joining me, and I hope you found this useful. And if you're interested in one-on-one tutoring, then check me out on thephysicscoach.com. Mahalo.